Hi, I'm Zor. Welcome to Unizor Education. Today we will talk about practical implementation of certain Lagrangian approaches which we were talking about last time. And today we'll talk about very practical example from classic physics, pendulum. Well, actually it's two problems. One is simple, another is a little bit more complex. And both are supposed to illustrate how Lagrangian can be used, and in the second example you will see how simple it is to use it in a complicated case. Okay, so this lecture is part of the course called Physics Plus. It's presented on unizor.com, and as I was just talking, there are previous lectures, there is a subsequent lectures. They're all related, and that's why I suggest you to watch it as a course, actually, one lecture after another, because they are logically related to each other. So you go to unizor.com, choose the course Physics Plus. Now this part of the course is called Lagrangian, and this is one of the lectures in that course. You will see all of them, actually. Now the website is totally free. There are no advertisement. Sign in is optional. So basically it's all free for all, and all for free. Now also there are prerequisite courses. There is a math for teens and there is a physics for teens. Both kind of precede this. There is also a relativity course. So it's relatively rich in the contents website, and that's why I suggest you to use the website rather than, if you find it, for example, this lecture on YouTube, you will just have one lecture and there is no subsequent or previous lectures, etc. On unizor.com you have basically the whole curriculum. Okay, so pendulum is a relatively simple task which can be approached from both the Newtonian mechanics and Lagrangian mechanics. Now, from Newtonian mechanics, if this is the pendulum, obviously this is a thread which is unstretchable. Now there is a object of certain mass, and let's say the length of this thread is L. Now there are, from Newtonian position, there are two forces. There is a force of the weight, which is mg, and there is a tension of the cord, of the thread, and together they are giving the force, which is always perpendicular to the thread because it goes along the circle, and the thread is actually a radius of this circle. So trajectory, the force is parallel to trajectory is circle, and that's why it's a perpendicular, which means that this is perpendicular as well, because this is parallelogram of forces. And so this particular force is equal to weight, which is mg, times, if this is angle alpha, this is angle alpha, this is angle alpha, so it will be sine of alpha. All right. Now the force in turn is basically m times acceleration, according to Newtonian mechanics, the second Newton's law, and the acceleration is actually can be expressed in terms of angle alpha as well, this is the first derivative of the speed, linear speed. Linear speed is radius times angular speed, and one more derivative would be this, from which we get this equation L alpha second derivative is equal to well, m, this m, equal to mg sine of alpha. M cancels, and alpha is equal to g over L sine alpha. So this kind of well, actually, I think we need a minus sign, if I'm not mistaken, because of the direction of the down. Well, doesn't matter. We're talking about, at least we're talking about absolute value of this. So it's a relatively easy solvable problem. However, you cannot actually solve this particular equation in regular functions which we are used to. The solution to this is some kind of a complicated elliptical function, which is not really like a formula. But in case angle alpha is very small, sine of alpha is approximated as alpha itself, and so it will be, this is second derivative and this is just plain alpha, so harmonic oscillation would be a solution to this differential equation. Okay, now we have only one particular variable which is changing with the time, which is angle alpha. Let's approach exactly the same problem using Lagrangian. Okay, Lagrangian is, first of all, we have to construct Lagrangian, which is kinetic energy minus potential energy. Okay? Now, kinetic energy is mv square, which is actually 1/2, which is actually same as this. V square would be L alpha prime derivative square. So that's my kinetic energy. Now my potential energy is, well, the height of this particular object over, let's say this is the ground level, and this is the beginning, this is, let's say, h, the height. Now, so we have to subtract from the total h, we have to subtract this, which is L times cosine. So h minus L times cosine of alpha, this is a height above the ground, and if we will multiply it by mg, we will have the potential energy. So we have kinetic energy, we have potential energy. Now, the next thing is to use Euler-Lagrange equation, and that would be basically the equation of motion. Now, the Euler-Lagrange equation is this. The only variable right now which is changing with the time is alpha. So this would be Euler-Lagrange equation. Partial derivative by alpha is equal to time derivative of partial derivative of alpha prime. Okay, so what's interesting is alpha is only in the potential energy and alpha prime only in kinetic energy. So the way how it goes is, first of all, so from kinetic energy we get only this one, right? Okay, and this is from potential. Potential is this, with a minus sign, by the way. Right, it's a minus sign. So that would be derivative of this. Now this is a constant, so minus, and derivative of cosine is sine. So it would be what? Minus sine L. Minus L sine alpha, I think. Right. Okay. Now, on the right side, it would be derivative by this, and that would be only from this one. So it would be equal to square would be 2 and 1/2 is cancelled, so it would be L square alpha prime. That would be the partial derivative, and then by time it will be another derivative here. And by the way, I forgot to put mg here. Minus, I think. Okay. And mass also here, I forgot. So it's mass here as well. So mass is cancelling out, and we have 1L is also cancelling out. Alpha blah blah is equal to minus L over G sine alpha, which is the same thing as this one. So it's a little bit longer maybe than this one, but again, it's a simple problem. My purpose right now is to present a more complicated problem and demonstrate how easier it is with Lagrangian to solve it. Okay, so let's wipe out all this and go to a more complicated problem. Now, more complicated problem is almost the same, but instead of unstretchable thread, I will have some kind of a tube here and a spring. Now, tube is so spring doesn't really bend itself, so it's unbendable because it's within this tube. Let's say it's a glass tube, so you will see what's happening. But since it's a spring, this particular object has 2 degrees of freedom. First, it goes like pendulum, and second, it goes within this tube back and forth because the spring might actually do some kind of oscillation itself. So it's 2 different degrees of freedom. L now is L of t, and L is L of t, and alpha is alpha of t. Both are functions of time. So it's 2 degrees of freedom. Now, I'm not going to do anything with Newton's approach. It's kind of complicated, and if you want, well, please do it. If you can send me completely good solution, I will publish it on my website with reference to you. Okay. Now, so let's approach this only from the Lagrangian standpoint. Now, for this, again, we have to calculate kinetic and potential energy. Okay. First of all, it's very important right now would be the speed of this thing as a vector. Now, since we have 2 different degrees of freedom, one would be like this and another within the tube, I will represent the vector v as 2 vectors. One is parallel to the spring, and another is perpendicular to the spring. Now, the parallel to the spring goes this way, perpendicular to the spring goes this way, so these 2 vectors are perpendicular to each other. Because this v perpendicular goes along the tangent of the circle, and this goes along the radius. The parallel goes along the radius, so they are perpendicular to each other. Well, since they are perpendicular, their length is much easier to calculate. We don't need the vectors formula. So plane without the arrow is just the length of this vector. So that's easier. Now, why do I need it this way? For kinetic energy purposes. Because kinetic energy is mv squared over 2. I can very easily, because it's a Pythagorean theorem, say that this is this one plus this one. It's easier to calculate it this way, to express this in terms of L and alpha. Now, what is V parallel? Well, V parallel, the speed within this thing, well, it's just L prime of t. It's a speed of changing the length. Well, length is L, so the speed is the first derivative. That's it, very easy. And what is my perpendicular speed? That we already did in the previous lecture. It's L of t times alpha prime of t. Angular speed times radius. So we have relatively easy expression for both of them, and kinetic energy is done. Okay? So kinetic energy is equal to 1/2 mass and sum of and this v square, which is sum of these two. So we have L prime square plus L square alpha prime square. I dropped functions of t just for brevity, but you understand that all of these are functions of t. L is function of t and alpha is function of t. This is first derivative of L, this is first derivative of alpha. Now, potential energy. Potential energy actually is not much different from before if it's related to the gravitation field. So potential energy related to gravitational field is the same as it was before. So it's mg times h minus L cosine alpha. So this is L cosine alpha. H is height of the top of the ground. So that's exactly the same as before. The only thing now, L is also variable as well as alpha. Let me write it down a little bit more accurately. Gravitation is equal to mg h minus L cosine alpha. But also we have a spring. Now if you remember, the spring potential energy is equal to 1/2 k x square, and x square was a displacement from the neutral position. So in our case, let's consider that the length of the neutral position is L0, it's a constant. So we have L minus L0 square. L is a function of time, L0 is a constant. So we have now sum of these is my potential energy. mg h minus L cosine alpha plus 1/2 k L minus L0 square. So we have potential, we have kinetic. So all we do right now is write down the Euler-Lagrange equation. The problem is that we used to have this Euler-Lagrange equation for the problems with only one degree of freedom, one variable. Now we have two variables, L and alpha, the lengths of the spring and angle. Well, the beauty of the whole thing with Lagrangian in complicated cases like this is that you can actually construct two different Lagrangians. One is using like L only as a variable, disregarding the fact that alpha is variable. And another Lagrangian is about another degree of freedom, alpha. Again, disregarding that L is a function of t, of time. So we will have a system of two Lagrangians, and again, we are just, it's technicality. We just do the partial derivative without any kind of hesitations, and we will have two different equations. So let's go the first one. The first one is by L, let's say. Okay, so it's d by L of Lagrangian, which now depends on L, L prime, alpha, and alpha prime, should be equal to d by dt, d by dl prime of this Lagrangian, of the same Lagrangian. So that's the formula. And the second equation would be the same thing, except I will use alpha and alpha prime here. Okay, so well, let's just construct it. So L is a difference between kinetic energy and potential. So first we do d by dl, which is, so we disregard this piece because it's not dependent on L, it depends on L prime, and only this one. So we have L square by L, so it would be m L alpha prime square, right? That's the derivative by L, partial derivative by L. Now, partial derivative by L of this thing, this is potential energy. This depends on L and this depends on L. So, but it would be with a minus sign, right? Because it's kinetic minus potential. So minus and this minus would be plus. So it would be plus. By L it would be mg cosine alpha, just like this. The derivative by L would be, no, it would be minus, and minus would be plus, right? And derivative of this would be, now this is plus, but that would, minus was in front of it, so it would be minus 2, and 2 would be k L minus L is 0, all right? Yeah, that's it. So that's the left part of it, that's this one. Now the right part is derivative of Lagrangian by L prime. So it should be equal to, kinetic by prime would be m L prime, right? By potential, there is no L prime in potential, so there is nothing here. And now we have to have a derivative by time, so I will just add another derivative here. So that's my first Euler-Lagrange equation, only for L. Now we will do exactly the same by alpha and alpha prime. So kinetic by alpha, it's this one. So we will have m L square alpha prime. All right. ml square and 1/2 of, yeah, looks like this, minus potential does not have alpha prime at all. Okay, so the equal sign, and now on the right side would be d per dt of, oh, I'm sorry, this is by alpha, not by alpha prime. The left part is by alpha. Oh, and this one doesn't contain alpha, so that's not. By alpha we have this one with a minus sign, and only this one contains. Okay, so it's minus because it's minus potential. This minus gives me plus. Then it would be L, and derivative of cosine is minus sine, so it would be with a minus, I think. Yes, that would be on the left side. Okay. On the right side it would be by alpha prime, which is this one. Alpha prime is, as I was saying, m L square alpha prime, and then by dt it would be another. I think I forgot mg here. Yes, mg, have to multiply. Alright, so what will we have? M cancels, L cancels, and we have alpha prime equal minus g over L sine alpha. Exactly the same as for the unstretchable thread instead of a spring. So as soon as we kind of ignored the dependency on L, the second Lagrangian, the second Euler-Lagrange equation from the Lagrangian, we will get exactly the same. It's not a coincidence, that's basically by design. Now, to warm up your expectations, the next lecture I will talk about why this is kind of separation, why this is happening. So we will talk about generalized coordinates, and you will see how this Lagrangian, which depends on more than one variable, like more than 1 degree of freedom, in this case it's 2 degrees of freedom, L and alpha, how it can be, how Euler-Lagrange equation can be established for each degree of freedom, actually. But that's the next lecture. So here I'm just using this to demonstrate that the whole thing actually we have reduced to, in this case, system of two Euler-Lagrange equations, because there are 2 degrees of freedom. And again, I don't want to really do anything in the Newtonian mechanics because it would be more complicated. The more complicated the problem is, the easier it is to use Lagrangian mechanics instead of Newtonian. Well, basically that's it. My purpose was to demonstrate the usage of Lagrangian and Lagrangian mechanics in a slightly more complicated cases. And quite frankly, in physics everything is complicated. Something like quantum mechanics, it's really started from Lagrangian, and there are a lot of very interesting theorems which can be actually proven using Lagrangian. Like, for instance, the theorems about how the conservation laws, like energy conservation or moment conservation, are related to symmetry of our space, to basically isotropness of our space. Okay, so that's it. I suggest you to read notes for this lecture. It's the same website, the same page which you will find the video presentation, and parallel to it the notes. So notes contain basically a little bit more detailed calculations, but basically the same thing. and every lecture actually has notes. In some cases, I actually have the exams, which you can take as many times as you want until you will get the perfect score. Well, that's it for today. Thank you very much, and good luck.